Now, I'd like to convince you that where we're going is exactly where we've been. If I were to take a ball and throw it straight up at 20 meters per second, how many seconds before it stops at the top? Shout it out. 2. A mighty shout goes up in the land. Okay, 2. How do we know that? Because it starts with 20, and every second that goes by, we add 9.8, let's call it 10 meters per second down. Well, it's going to take us 2 seconds to whittle away at 20. Okay? Now, let's look at a different example. Suppose I have a wheel that is rotating like that, such that the omega vector, the red omega vector, is pointing by right-hand rule towards you. And it's slowing down so that the alpha is away from you. Now, this didn't used to be cut off. It was nice and beautiful until we got a new version of PowerPoint. Bill Gates did that to me. You'd think a multi-million billionaire would have better things to do than pick on me, but there you go. Now, I'm not real good at drawing things in 3 dimensions like that, so I'm just going to take that wheel and make it flat on the page. But that means I'm going to need to represent vectors that are coming out of the page and vectors that are going into the page. Now, there is an accepted way of doing that. A vector that's coming out of the page, we draw this way, and this represents the point of the arrow coming out towards you, straight out of the page. This vector is going into the page, away from you, and you see the feathers at the tail end of the arrow going away from you. Now, suppose I told you that this wheel started with an omega that was 4 pi radians per second. Just as an aside, how many times is that going around each second? 2. Twice, okay? If it has an alpha in the opposite direction, it's slowing down. If that alpha has a magnitude of pi radians per second every second, how many seconds before this wheel stops? Shout it out!
4.
4. All right, you got it. You got it. One more connection. This wheel of serious injury here. If I get it sped up here, so that its omega by right-hand rule is right out along that post, well, this wheel is weighted so that it doesn't want to slow down. So the spin rate stays the same. Now the spin rate tells me how long the omega vector is. It's not speeding up, it's not slowing down. The omega vector is not getting longer, it's not getting shorter. It always points out along that bar. Is the omega vector changing?
Yes.
Yeah, it's changing direction. And because the omega vector is not getting longer and not getting shorter, the alpha cannot be along the direction of omega or opposite the direction of omega. The only direction left is perpendicular to omega. So I have a little representation here. Let me spin this up again. Again, if this were Harvard, we'd have a machine or a grad student to do that. Okay, so the omega vector is always pointing along the red arrow, and it never gets longer or shorter. The alpha vector is the blue arrow. It's always 90 degrees to the red arrow. What does this remind you of in the linear kinematics case? Talk to your neighbor. Talk to Nimrod. Okay. Brave soul, what does it remind you of? Raise your hand.
Centripetal acceleration.
Centripetal acceleration when you're going around in a circle. Okay? If you put cruise control on and you go around in a circle, you don't change the length of your velocity vector. But you are changing the direction of the velocity vector, and that means your acceleration vector has to point 90 degrees, which in a circular case is towards the center, and hence we call it centripetal or center seeking. Okay. Now here's the magic. Here's the big connection. The definition of linear velocity was how far we got down the road in a second. The definition of angular velocity is how far we get around the wheel in a second. And because those definitions all look so the same, they have the same relationships, we find that the kinematic equations look the same. The first kinematic equation looks like that. And you see, everywhere we have a linear velocity, we replace it with a rotational velocity. Wherever we have a linear acceleration, we replace it with an angular acceleration, and time is time. But all four of my kinematic equations have a rotational analog, and all I have to do is make the replacement between the linear, like in this case delta x, with the rotational delta theta. Now, we solve linear kinematic equations by making a list. We make a list of the 5 players and that list always looks the same. We've got delta x, we've got A, we've got B initial, B final, and delta t. And we have to find 3 of these from our problem statement in order to solve for the other 2. Well, in rotational kinematic problems, we have the same list, but with their analogs. Instead of delta x, we have delta theta. Instead of A, we have alpha. Instead of V, we have omega, initial and final. And time is time. And you have to find 3 of those from the problem statement.